right, welcome back, everybody. So this part of lecture, I want to look at a few um, synthesis examples. So on this first page here, I just have all four of them that I'm going to work through written out. So if you want to, pause this and try to work out some of them on your own, I'm going to go ahead then and on the next slides, go ahead and work through these. Okay, so let's go ahead and look at the first synthesis problem. Okay, so what I would probably first do is map the carbons in the starting material to the carbons in the product. So notice how this carbon here has this methyl group, attached to it. So it's likely that that's that carbon in the product. Okay, so let's operate under that assumption. Okay, and so basically what we need to figure out is how do I move an alkene from one side of the molecule to the other. Okay, and so it's a very common series of reactions to basically add a halide and remove a halide through the subsequent electrophilic addition to alkenes followed by E2 eliminations. Okay, so what I want to think about first then is, well, how could I, at least get a functional group onto carbon 2? So I want to think about a Markovnikov addition on carbon 2. Okay, so I'm going to do HBr here. And the reason why I'm choosing HBr is because I want to get the Markovnikov bromide, because then I can utilize that Markovnikov bromide to do a subsequent elimination. Okay, so from here I have this tertiary halide. Okay, and so now I can, walk the double bond sequentially down the carbon chain, and I can move it into that highlighted position. Okay, so I can do that through an E2 elimination. Okay, so you could really choose any E2 conditions here other than using a bulky base because we want Zaitsev's product in this case. So I'm going to use NaOH, H2O, and heat. Okay, and now I've moved the double bond one step closer, and now we're just basically going to repeat those steps. But now I need to get my halide at carbon 3. Okay, so rather than have the Markovnikov bromide like I have in this case, I want the anti-Markovnikov bromide where I've placed the halide at that position so that I could then do the elimination from that point. Okay, so now I still want to use HBr, but I'm going to shuttle this through the free radical reaction by adding our free radical initiator peroxides and then heat or light. Okay, so that's going to give me the halogen at this, what we labeled carbon 3. And now we're just one E2 elimination away. And so now it actually matters what type of base we use because we have the potential to form the alkene on either the Zaitsev or the Hofmann position. And, the product that we're trying to arrive at, that is shown is clearly the Hofmann product. So here I need to use either LDA or tert butoxide to arrive at that Hofmann product. Okay, so this series of steps of kind of, walking the alkene down the chain is very common. Okay, so again, we saw, let me get that back in there. Okay, so what we saw was, we added the halogen and then we eliminated, added the halogen, eliminated. Okay, so that's a very common series of steps in synthesis, especially coming from the reactions that we've seen in the last couple of chapters. Okay, so let's go ahead and look at our next synthesis question. Okay, so a few things about this one. So the first one is our starting material is an alkane. So I want you to ask yourself, what is the only reaction of alkanes that we know of? Because that is going to tell us how we are going to start this synthesis. Okay, and then the other thing is, let's go ahead and map some of the carbons. Okay, so it's likely that, carbon 1 and 2 are there and that we're adding a bond between carbons 2 and carbon 3. So you know that acetylide substitution is going to be a player here because that's the only way we know how to make carbon-carbon bonds. Okay, so back to my other question. So what is the only reaction of alkanes that we know? Well, it's Br2 and light through free radical halogenation, right? And so what was this regioselectivity of those free radical reactions? So we added the halogen at the most substituted carbon. Okay, so I got to that tertiary bromide. Okay, and so now let's think about what needs to be present at carbon 2 and carbon 3 to form that bond. Well, one of them needs a leaving group and one of them needs to be the nucleophile. Okay, so I'm going to propose that carbon 2 bears the leaving group and carbon 3 is going to be the carbon of acetylide. And you can rationalize that because you wouldn't be able to have a triple bond here because you would have 5 bonds at that carbon. And so the triple bond has to be coming in, between carbon 3 and 4. That would be fine. Okay, so now we're kind of in a similar place in synthesis as we were in our previous example, because I basically need, instead of having, the bromide at the position it is, I need it at that corresponding anti-Markovnikov position. Okay, so what I'm going to do is, well, I need to go through the alkene, right? So the alkene is going to be the intermediate between the Markovnikov and anti-Markovnikov products that I'm moving back and forth between. Okay, so again, I need the Hofmann product. So I'm going to choose LDA or tert butoxide here. And now I can add my HBr with peroxides to form the anti-Markovnikov product. Okay, and now I can go ahead and add my carbons. I'm going to do that directly with using acetylide as a reagent. Okay, so we can add our favorite polar aprotic solvent to facilitate that SN2 reaction. Okay, now we've added all the carbons that we need. Okay, so let me just count them so you can see them. So there's carbon 1, 2, 3, and 4. So we added carbons 3 and 4 there through this acetylide substitution. And then lastly, we have to remember how is it that I go from alkyne to alkane, and the reduction I want through is H2 and platinum, or palladium or nickel. Okay, so just to recap a few things that were important there. So one was, if you're starting with an alkane in your synthesis, you know that the first reaction you're doing is Br2 and light, because that's the only reaction of alkenes that we know. Another thing that we saw is, what is the intermediate between a mark and an anti-mark halide? So the intermediate is this alkene. So I know if I'm able to make the mark product and I need the anti-mark product, that the alkene could be the intermediate, synthesis intermediate. And then lastly, when I was thinking about making that carbon-carbon bond between carbon 2 and 3, I chose which carbon was the acetylide and which carbon had the leaving group based on the substitution. Okay, so let's move on to number 3. So in number 3, we're not adding any carbons here, but we are modifying the functional groups. So notice how we have basically at carbon 1, we have formed a ketone. And so, something that you could do to start off your synthesis is think about the ways we know how to make ketones. So one of them would be hydration of an alkyne. Okay, and one of them would be oxidation of an alcohol. And then the other way would be ozonolysis or HIO4 cleavage. Okay, and so that one doesn't make so much sense because I'm not changing the number of carbons, but you could actually complete the synthesis through either of the first two methods. So I'll go through both of those syntheses. Okay, so we could hydrate an alkyne, or we could oxidize an alcohol. I'll go ahead and do the oxidation of an alcohol method first, because that reaction is the most fresh in our, in our minds. We just talked about it earlier today. So let's go ahead and do that. So if I was going to utilize that, let's just think about that as the last step. Okay, so here it doesn't matter actually which oxidation you use, PCC, dichromate, Jones, any of those, since the corresponding starting material will be a secondary alcohol. Okay, and so now we've shortened our synthesis by a step because this is my new target molecule, this benzylic alcohol. And so we need to think about how can I convert that starting material to that alcohol. So again, treat this starting material as essentially an alkane, because we don't touch benzene, right? So basically treat carbon 1 and 2 as our alkane, and the benzene just as a substituent. And so the first reaction that we're going to do is the only reaction of alkanes that we know. So still it's going to be Br2 and light, and that's going to give us that benzylic bromide. Okay, and now that I have the benzylic bromide, I really need to ask, well, how do I convert a bromide into an alcohol? So you could potentially argue an SN2 here, but I'm actually going to do it in a slightly different way. I'm going to go ahead and go through the alkene intermediate and then follow that up by hydration. So in my opinion, going from a secondary halide to a secondary alcohol, it's better to do elimination followed by addition rather than try to do the SN2 substitution, because you don't want to have to deal with the competing E2 reaction. So I'm going to go ahead and just do the E2. You can use any base here, but I'm going to use a bulky base to avoid any sort of potential for the SN2 reaction. And now we're basically going to think about, how do I make a Markovnikov alcohol from an alkene? There's lots of methods you could do here, but the easiest one to write out is H2O and H+ to do acid catalyzed hydration. Okay, so that was the method of oxidation of an alcohol. So what would be the other way? So the other way is actually going to come from this same intermediate, one of the same intermediates. We're going to take this alkene, okay, and what we're going to do is we're going to do alkene to alkyne synthesis and then do the alkyne hydration. So I'm going to go ahead and do this in a different color, but if I was going to do alkene to alkyne synthesis, remember I'm going to do Br2 to arrive at the, dang it, okay. All right, so I'm going to do Br2 and dichloromethane to end up at the dihalide. All right, and then I can do my double dehydrohalogenation to end up at the alkyne. Okay, so here I need 3 equivalents of NaNH2 in NH3, and then I need a workup step because I'm not adding any carbons here. Okay, so that's going to give me the alkyne. Okay, and now I just need to do alkyne hydration. And so now I have to think about how do I do Markovnikov addition or Markovnikov hydration. And so this is where I need mercuric sulfate, H2SO4, and water to give me the product that was observed. Okay, so either of these methods, would be fine. You can see that one of them's slightly shorter than the other. So the first one we looked at, oxidation of an alcohol, ended up being a few fewer steps. So that would probably be the preferred synthesis. Okay, so that was the third one. Let's go ahead and do the last one here. Okay, so the last one is going to incorporate a lot of the ideas that we've seen in synthesis so far. So again, one of the first few things that I would do when I'm looking at a synthesis is think about where the carbons in the starting material are. So you can rationalize, that carbons 1 through 4 that I've labeled in the product are coming from the starting material. It's pretty unlikely to do a carbon-carbon bond cleaving reaction unless your final products are going to be the products directly coming out of ozonolysis or periodic acid cleavage. So we can assume that those 4 carbons are the ones from the starting material. And then that means that I'm basically making an ether. Okay, so here I want you to think about ways that we know how to make ethers. There's really 2 ways. One of them comes from the variation of acid catalyzed hydration with an alcohol, of an alkene. And so the reason why we're going to not use that method is because that follows Markovnikov's rule. So there's no way to make the ether on the less substituted carbon, so carbon 4 rather than carbon 3. So then the other way, and this is the way we're going to use, is going to be Williamson ether synthesis, which is an SN2 step. Okay, so that's how we're going to think about making that ether. Okay, so first thing, what reaction do we know has to be first? Well, it has to be Br2 in light because we're starting with an alkane. Okay, and now essentially we need to take our bromide at carbon 2 and somehow get it over to carbon 4 to either make that the leaving group to do the Williamson ether synthesis or to turn it into the alcohol, and then I can make the alkoxide. So I'm going to go ahead and try to get that bromine onto carbon 4, and then I'm going to do an SN2 with the oxygen anion, of basically this molecule. Okay. So let's go ahead and start moving that halide over to that N carbon. So again, I'm going to start with an E2. Here I want Zaitsev product, so I need to use not a bulky base. Okay, and then I'm going to do anti-mark addition. So HBr, peroxides, heat or light. That gives me that secondary bromide. And then again, I'm going to follow that up with LDA to get to a Hoffman product. And then I'm going to repeat my HBr and peroxide steps. I guess I'll be consistent and use light for all of those. Okay, and so now I'm ready to go ahead and do my SN2 step. Okay, so I've walked my leaving group all the way down the carbon chain through this, series of addition, elimination, and we're walking, that halide all the way down the carbon chain. And so now I can think about what nucleophile I need. So I would need this oxygen anion. Okay, so that's isopropoxide. And then we can add our favorite polar aprotic solvent to do our SN2 step. And this is directly going to give us our product. Okay, I realized the methyl group got deleted there, so I added that back in. Okay, so just again to think about, some strategy when you're mapping out your synthesis. So one is to think about your starting material and what reactions you have available to you. If you're starting with an alkane, you're starting with BR2 and light or Cl2 and light, but usually BR2 and light because it's the one that is regioselective. And so you'll find the most substituted halogen, and then you can, in this case, we needed to move that from carbon 2 all the way to carbon 4 to facilitate the Williamson ether synthesis and do the SN2 step. All right, so that's all I have planned for today. And so I hope you guys get some practice in doing synthesis. It's a really good way to practice your reactions and recall of reagents. There's tons of synthesis problems in the workbook at the end of chapter 10, and as well as the textbook in the end of chapters 8, 9, and 10. So there's lots of places to get practice with doing these synthesis reactions, and I'm happy, or synthesis problems, and I'm happy, of course, to go through any sort of synthesis in office hours.